When we designed anything, from a bridge to an airplane wing, we need to understand how forces are distributed within the material. These internal forces are what we call stress. But the stress at a single point isn't just one number. It changes depending on the direction you're looking from. Today, we're going to explore how to find the specific angles where these stresses are at their most extreme. Imagine zooming in on a tiny piece of a loaded material. We can represent the state of stress at that point with a small square element. There are normal stresses, labeled with the Greek letter sigma, which pull the element apart or push it together. And there are shear stresses, labeled tau, which try to slide one face past another. But here's the crucial idea. If we cut our tiny element at a different angle, the stresses on those new faces will be different. Notice how the pulling and sliding forces change as we rotate our perspective. This raises a critical question for any engineer. At what angle is the material being pulled apart the most? That's the angle where failure, like a crack, is most likely to begin. To answer this, we don't have to guess. These are the stress transformation equations. They look a bit intimidating, but all they do is tell us the new normal stress, sigma x prime, and the new shear stress, tau xy prime, for any angle of rotation, theta. Our goal is to find the angle theta that makes this top equation, for the normal stress, as large as possible. And if you remember from calculus, how do we find the maximum or minimum of a function? We take its derivative and set it equal to 0. We're looking for the flat peak of the stress curve. The first term is a constant, so its derivative is 0. For the second term, the derivative of cosine is negative sine, and by the chain rule, a 2 comes out. For the third term, the derivative of sine is cosine, and again a 2 comes out. Setting this whole expression to 0 gives us this relationship. Now we just need to solve for the angle. We'll move one term to the other side of the equation, and if we rearrange it to get sine over cosine, we get the tangent. This beautiful result gives us the orientation of the so-called principal planes, the planes where the normal stress is at a maximum or minimum. We call this special angle theta p for principal. We can think of this tangent relationship as defining a triangle. The angle is 2 theta p, the opposite side is 2 tau xy, and the adjacent side is sigma x minus sigma y. This triangle is the key. It holds all the information we need to find the magnitude of the maximum stress. Using this triangle, we can write expressions for the sine and cosine of 2 theta p. Now, we substitute these back into our original stress transformation equation. It looks like it's getting more complicated, but watch what happens. Let's define a term r, which is half the length of that hypotenuse. Now our sine and cosine expressions are cleaner. Plugging these in, we can combine the last two terms. The expression inside the bracket is just r squared, so the whole thing simplifies beautifully. This gives us the values of the maximum and minimum normal stresses, which we call sigma 1 and sigma 2. Excellent! We found the maximum pulling stress. But what about the maximum shearing or sliding stress? The process is exactly the same. We take the transformation equation for shear stress, find its derivative with respect to theta, and set it to 0. After differentiating and simplifying, we get this expression for the angle of maximum shear, which we'll call theta s. This looks very similar to the angle we found for the principal stresses, but notice it's the negative reciprocal. If we plug this angle back into the shear stress equation, the magnitude we find for the maximum shear stress is simply our old friend r. An even more elegant way to see it is that the maximum shear stress is just half the difference between the maximum and minimum principal stresses. This negative reciprocal relationship between the tangents is a big giveaway. It tells us that the angle 2 theta s and 2 theta p are 90 degrees apart. This means the planes of maximum shear are always oriented exactly 45 degrees away from the planes of principal stress. They are intrinsically linked. So, we found the orientation for maximum shear. But is there any normal stress on that plane? Not quite 0. If we plug the angle theta s back into the normal stress equation, a wonderful cancellation occurs, and we're left with this simple term. This is the average of the original normal stresses. So to summarize, at any point in a material, there are two special orientations. One, the principal orientation, is where the normal stress is maximized and the shear stress is zero. The other, found by rotating 45 degrees, is where the shear forces are at their peak and the normal force is simply the average.